Welcome. So, a couple of days ago, we learned the difference between a null and an alternative hypothesis, and and we also learned when we reject and when not to reject that null hypothesis based on their p-value and the alpha level. So now today, we are going to learn how to do our very own one proportion z-test. And what this will allow us to do is calculate our very own p-value and determine if that p-value is significant or not. So our learning targets are: I can state and check the random, 10% and large counts conditions before conducting a significance test. And 2, I can conduct a significance test on the single proportion using a one prop z-test. So let's go over potatoes. The potato chip producer is just received a truckload of potatoes from its main supplier. If the producer finds convincing evidence that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load from the supplier. A supervisor selects a random sample of 500 potatoes from the truck, and the inspection reveals that 47 of those potatoes have blemishes. Carry out a significance test at the significance level. What should the producer conclude? So, when you're conducting a one proportion z-test, you should always first state your hypothesis. Our hypothesis in this case is our null is that p equals 0.8. We are fine with our potatoes being 8% with blemishes. What we aren't fine is if more than 8% for potatoes have blemishes. So our alternative hypothesis in this case is p is greater than 0.08, where p is a proportion of potatoes with blemishes. So again, we're assuming that 8% of our potato population have blemishes, and if it has any more than that, we reject our potato shipment. So one important thing is how we sort of look at our hypothesis testing is if the alternative hypothesis is greater than or less than, we are conducting a one-tailed test. So when we are looking for a p-value less than our null hypothesis with an alpha of 0.05, we're essentially looking at that blue shaded region on the left, and we are calculating the likelihood of something showing up in that blue region. Same with p greater than. We are assuming that our p is going to be around 0, and we are looking for the likeliness of getting a result in that blue region again. So anytime you see a z-score, why are we doing z-scores? Well, continue on the video, and anytime you see a z-score less than negative 1.645 or greater than 1.645, that's sort of like the rejection zone. That is, where you can feel comfortable rejecting a null hypothesis. But we also looked at if the alternative hypothesis is not equal, we're conducting a two-tailed test. So we're looking at the likelihood of something happening 0.025 of the time on both sides of our zero. So we're looking for the likeliness of it happening on either side of that zero. And so that sort of gives you a better visual of what's happening when we conduct our test. We're looking for where our actual test statistic lies on this curve right here. And remember, everything needs to be set to a normal curve. So step 2, we're going to check our assumptions. And just like any other calculations we've done in the past, we are checking for the same 3 things. 1, is it random? Yes, because we just randomly selected 500 random potatoes. Is our sample 10% of the population? Well, it's a truckload of potatoes, so you can feel pretty comfortable in the fact that 500 is greater than 10% or less than 10% of our whole potato population of a truck. So yes. And is our MP greater than or equal to 10, and is n times 1 minus p greater than or equal to 10? So again, in this case, yes, it is. So 500 times 0.08 is greater than 10, and 500 times 0.92 is also greater than 10. So yes. And do you always check your assumptions? Yes. Because if they check out, we know we can fit our information to a normal curve. We need to put everything to approximately a normal curve. Everything in statistics is based off of this normal curve. And so right here is our normal curve, and we need to see the likeliness of it happening on the right side of this normal curve. So step 3, we need a calculator test statistic and our p-value. So when we're calculating our test statistic, it's hard to say. Calculate your test statistic and our p-value. We need to calculate actually a lot of different things. What do we need to calculate? Well, this is all stuff we've done before. We need to calculate the proportion of our sample. We need to calculate the standard deviation of our population parameter, and we need to calculate the z-score. So our sample proportion is going to be p hat is equal to 47. Remember, we found 47 out of 500 tomatoes with blemishes, and that equals 0.094. And our standard deviation of our population, just like any other standard deviation of a proportion, is going to be the square root of p times q. Remember, q is equal to 1 minus p over our sample size. So in the case of our potatoes, it's going to equal the square root of 0.08 times 0.92 over 500. And so remember, 0.08 is a proportion of potatoes with blemishes. 0.92 is 1 minus that over our sample size of 500. And our standard deviation is 0.012133. And so from all that, we can start calculating our z-score. So z-score in this case is going to be your p hat minus your p over your standard deviation. So our p hat, remember, is our sample proportion, so that's 0.094, minus our population proportion, which is 0.08, all divided by the standard deviation, which is 0.012133. So we calculated all that to get a final z-score of 1.154. So now that we have our test statistic, we need to see the likeliness of getting a test statistic of 1.154. And so you can use our calculator to do normal CDF to find the probability of getting a z-score of at least 1.15392. And we end up with a p-value of 0.1243. So that means there is a 0.1243 probability of getting our test statistic of at least 1.154. So on the AP Stat exams, you need to show all of your calculations, and you also need to show this normal curve that I have set up right here that I just showed you guys. So that shaded area is everything more than 1.54. You can just do a quick sketch as long as your mean is 0 and your standard deviations on either side of the curve is 1. So now we can finally conclude. Because our p-value 0.1243 is greater than the alpha of 0.05, we fail to reject our null hypothesis. There is not convincing evidence that more than 8% of a shipment of potatoes has blemishes. So with every conclusion, you are going to follow this exact sort of model. I have a sort of template set up for you on your guided notes, and that's a sort of guided template that you need to use to give essentially everything that they're looking for on their AP Stat exam. They're looking for your p-value. They're looking for the fact that you fail or or you fail to or not fail to reject a null hypothesis, and why you did not reject the null hypothesis. So again, we stated our p-value 0.12343, and we stated whether or not we rejected our null hypothesis, and we stated why we failed or not failed to reject our null hypothesis. So now let's do another example. So a large city's DMV, the Department of Motor Vehicles, claimed that 80% of our candidates passed driving tests. But a newspaper reporter's survey of 90 randomly selected local teens who had taken the test found only 68 who passed. So does this finding suggest that the pass rate for teenagers is lower than the DMV reported? Write appropriate hypotheses. So in this case, we are assuming that teenagers pass it 80% of the time, and we're looking for the likeliness of less than 80% of teenagers passing the driver's test. So that means we can set up our HO as P equals 0.8 and our HA as P is less than 0.8, where P is a proportion of teenagers who pass the driving test. How cool, that's hip. Everybody loves driving. Step 2, check your assumptions. So first, remember, randomization. Is it random? Yes, it's stated it was random. 10% condition. Well, surely 90 teenagers is less than 10% of the population of teenagers. If not, you might live in, well, a tribe, but I don't know, some low population community. So yes. And the large count, 0.8 times 90 is 72, and 0.2 times 90 is 18. So yes, those check out as well, because they need to be greater than 10, and they are greater than 10. So now, again, step 3, you gotta calculate your test statistics and your p-values. Remember, we need to calculate our p hat, our standard deviation, and then finally we can use those pieces of information to calculate our test statistics. So p hat is 68 divided by 90, and that gives us 0.756. Standard deviation is going to be 0.8 times 0.2 over 90, and our z-score is going to be p hat minus p divided by standard deviation. Our p hat is 0.756. Our population parameter is 0.8. And our standard deviation is 0.042. We plug that all into our calculator and we get negative 1.05. So when we plug that into our calculator using normal CDF, we find that our p-value is less than negative 1.05 14.6% of the time. And so that's how, again, you would show your work using this normal curve. You would show all the calculations for your p-hat, your standard deviation, your z-score, and then you would show this sort of curve to show the likeliness of your p-value. So finally, again, we can conclude because our p-value 0.146 is greater than our alpha level of 0.05, we do not reject the null hypothesis. There is not convincing evidence to say that the passing rate for teenagers taking the driving test is lower than 80%. So good for you guys passing that driver's test. So we're going to go get back to class and we're going to practice some more of this. And basically everything in the rest of this unit is sort of based off of this idea of hypothesis testing. So if you understand this, you will more than likely understand everything else, which is great. So I'll see you later.